Here, please. Okay, so today's topic is leveraging AI for knowledge graph in biomedical informatics. So I'll give a small introduction about the speaker. His name is Sydney Anuyah. He's a graduate research assistant at School of Informatics Computing. So he's a teaching assistant as well for a cloud computing class. So that's how I know him. So recently he published a paper on a knowledge graph. So I was reading his paper and then I thought it was about AI and LLM. So LLM is the next big thing coming. So I just invited him for the event and he kindly accepted the invitation. So today we'll see how knowledge graphs are contributing in bioinformatics and health informatics. So thank you.
So thank you all for listening and being here. I know it's not easy to take out like 6 p.m. after a long day of class. So please let's clap for ourselves. Yeah, so I'm going to want to thank all the organizers of this club. It's really a privilege to be invited. So just a brief introduction about myself. Okay. So I'm Sydney, and well, I graduated from my undergrad degree in 2019 with an American equivalent GPA of 3.46. Well, I studied electrical engineering, but then I knew that something was more and I needed money. So like what everyone would do, I looked up the top paying courses. I had a very bad experience with programming. And whenever I think back, when I saw in my 300 level that never again would I code, I'm laughing at myself right now because now almost all my life is all about code. Eventually I enrolled in an online master's degree, did financial engineering. So I really have a diverse field. And then now I'm doing data science. And my research was basically on gastroesophageal reflux disease, which is one of the major diseases that plagues Americans. I've been exposed to NLP and LLM research. So I do a lot of NLP and LLM research here. And I graduated from my master's degree at IU Indianapolis with a GPA of 3.94. Right now, I transitioned to the data science PhD and expected to graduate May 2027. Work experience, I worked in Amazon, I worked in like Indiana IoT. Those are places that I've worked here in the US. So that's just like a brief about me. So let's go directly into the talk. So can someone tell me what biomedical informatics is? Like any volunteers? What is it? This is the silence, you know. So all right. Just so we can kind of move on. No, I need someone to actually tell me what's biomedical informatics. We're not moving on. So who is going to tell me what it is? All right. So basically, when we talk about biomedical informatics, it's like a very broad subject. This involves all fields under biology, medical, and having to do with information. So think about biological information, medical information, clinical information, pharmaceutical information. All of this just comes under the broad umbrella of biomedical informatics. Now, if we look at the next slide, we have all seen what genetic sequencing is. You know, you have the ATG, and this is just how the codes in the body is kind of written. Everyone has a different gene structure. So now gene sequencing and how we can actually map this out is possible through biomedical informatics. So every one of you, which I believe, or most of you, would belong to biomedical informatics. You guys are doing really great work, and I applaud you guys for that. That's awesome. Also, electronic health records, where almost all hospitals, especially like in the US, are moving to. We can kind of see how we no longer just use papers or for MRI scans. We have all this automated. We all have, so for a patient, maybe this patient has his 2-month checkup, 1-month checkup, and all the information is all here. So this is possible because of the unison between software and medical information. So this is one of the aspects in bioinformatics. And if we want to look at the subfields, we can see bioinformatics, clinical informatics. This is just a few of them. Now, the significance of biomedical informatics, we can look at all these five. Is there anyone who has actually seen like a use case for the course they're studying? If no one raises their hand, I'm going to pick someone. And it's going to be a lady. All the ladies have straight faces right now. All right, okay. So one way we can use basic biomedical informatics is in improved patient care. Think about having to analogically collect like multiple pieces of information on like paper, and you have to go through 1,000 documents just to find out what's wrong with this person, when you can actually just press a click of a button and press analyze, and you can kind of find out that information, which will help medical practitioners to spend less time in delivering more efficient results. We can also work with accelerated research. Having a knowledge graph, which I'm going to go into, can help people who have no experience in the field to be able to pick out one or two nuances and be able to kind of get a broad overview of what the subject field is about. Also, cost and resource optimization. Think about having to analyze a report. Like today, my mother called me and she's been working on this report for almost a week. And then with AI, I was able to produce about 7 times the speed and produce a great accuracy for that report. Now, if someone is being paid that amount of money and we convert that money into that spend into using and developing these tools, how much more are we going to save cost and how much are we going to have resources optimized? So basically, this is the role of artificial intelligence. We have artificial intelligence in data processing and management. So think about all the electronic records, how each of them are going to be analyzed. I also worked on a research project on cancer, detecting cancer in breast mammographs and with convoluted neural networks. So this is just one of the advantages of AI. So AI can suggest like, oh, we need to look at this case, something that the doctor might miss, and it's in the database. Maybe someone came in for something and the AI suggests, oh, check this, check that, because these are all automated. So data processing is one of them. Predictive analysis, who are more likely to be susceptible to a particular disease than another person. What class of people have GERD more than another class of people, you understand? So this is notice that more Americans who eat burgers are susceptible to having GERD than people who eat more fresh and food from the grounds. We also to look at NLP for text mining, clinical notes, look at clinical notes, how are we going to analyze like this long text, especially doctor's handwriting? How many people love doctor's handwriting? It's very legible, and we can use AI using NLP to actually create this box where we can get this large information and also begin to analyze, pre-process, do many things with it. I just spoke about medical imaging analysis, where I did that project on. Also precision medicine and genomics. You can also look at drug discovery, and this has just so many of the applications that AI can help us to accomplish. Now I will go into knowledge graphs. So this time, well, does anyone know the concept of knowledge graphs?
Yeah.
All right, you want to try it? Yes.
I mean, essentially a way to store the data inside of a graphical format so that you can easily go through nodes with edges. Yeah.
Awesome. Clap for him, please. That's spot on. Yeah, so if he mentioned nodes, he mentioned edges. So this is a node. These are nodes. And now a node to a point, you understand? Like this is nodes what connects them are like edges. Do you understand? Or the relationship between them. So this is just an example of a knowledge graph in Neo4j. I know we can't see it. The point is not for you to see it. You understand? The point was just for you to just know how it looks like. So each of those nodes are related to each other through what we call a relationship. So now this is what was meant to be seen, right? This is BRCA1 protein dysfunction. BRCA1 is a gene in the breast. Am I right? Yes, I think yes. So now BRCA1 mutation causes a protein dysfunction, and this is like a known fact, right? And because I see this graph as someone who has no idea, I can easily say, oh, okay, BRCA1 mutation causes this, and this causes a cellular malfunction, which can aggravate breast cancer and which can also lead to breast cancer. So for someone who doesn't have breast cancer, we can see that cellular malfunction can lead or cause breast cancer. And also for someone who has, we can see that cellular malfunction can also aggravate breast cancer. So just within the small graph, we are able to extract so much information already. You understand? And we can see BRCA1 mutation is influenced by carcinogens. Sorry, that clipped out. So that was carcinogens that I had there. So if you are exposed to breast cancer causing agents, you can see that this will cause this, and this can aggravate this. You understand? So, which is a very interesting way to put information. Now, computers would like to see something like this, especially large language models. It's easier to train them on this kind of data than it is to just train them on just long sentences, you know. So knowledge graph, like he said, is just a data structure that represents information through nodes, which are the entities. So in that example, we saw carcinogens, we saw BRC1, protein dysfunction, cellular degeneration, we also saw breast cancer. Those are nodes. Then the edges itself are the relationships between them. So if we go back, we can see the edges, causes, influences, increases the risk of aggravate. And so in biomedical informatics, this graph basically helps us to see, like I wrote there, organize complex biological relationship for easy access. You understand? So we can easily see the relationship between genes. We can see the relationship with diseases, proteins. Now imagine a study that has been done by 10,000 professors. Someone studied disease, another group studied genes, another group studied proteins, another group studied symptoms. Now, having this knowledge graph, incorporating it into one body of knowledge will help us to understand the different nuances between the disease, between the genes, between the proteins, between the symptoms of one particular node, and how it relates and branches off to other different areas. So now I want to talk about natural language processing, which is NLP, and knowledge graph. So just to give like a foundational overview. So the first thing, if maybe you're trying to incorporate NLP into your research, I think, is there any undergraduate student here? Awesome, it's nice to have you guys. So if you're an undergraduate student, you know, it's good you get to have more opportunities to maybe do your graduate degree, you understand, and work more on research. But most of us who are graduate students already work on research. And if you are looking at working in the field of biomedical engineering and also want to integrate AI, so these are possible scenarios that you can work on. One is named entity recognition. So named entity recognition is just I'm going to just explain this text by using this diagram. So if you look at this expression, this expression of NT3 in supporting cells in embryos preserve BRN3C null mutants. So now what you are trying to do now is trying to pick out the entities and naming each of them. Like using this one, this is just a normal English word. We don't necessarily need it. Expression, and this is just, this part is not necessarily what contains information in the sentence. In a sentence, usually 65% of it doesn't contain any useful information. It's just only very few parts. Now, so NT3 is a gene. Now, this is the information we need. Do you understand? Supporting cell is what is more or less like labeled as cell, and then you have mutant organisms. So these are things that you can do for thousands of sentences. There are definitely ways that the language model will now be able to help you through it. For instance, an average research paper contains about 300 to 3,000 sentences. So that is between, like, a 6-page research paper will contain about 300 sentences, and then a 60-page research paper, especially those review papers, contain almost about 3,000 sentences. Now, imagine you have about 10,000 of those. Do you understand? Like, that's a lot. It counts, it adds up. But if you look at statistical significance, you only need a subset. You understand? You just need a small sample. So what you need to do is just to do this named entity recognition for a few samples. And then you put it in maybe a natural language processing tool. Like for me, when I was doing my project, I did this with BioBird. BioBird it worked really well. It gave me over an 80-something% accuracy. So it was able to actually give me the names of each of the entities in my sentence. Like that, and that was great progress for me, because what happened was that maybe I trained 1,000 data sentences, and BioBird was able to run on 300,000 sentences. So I didn't need to go through 300,000 sentences myself to actually get this named entity recognition to plot my knowledge graph. So if I'm just going to read this, it just involves identifying and categorizing key entities within unstructured text. So I think we all understand what named entity recognition looks like. And if you want to say the use cases can be in disease identification, like recognizing, maybe I use Alzheimer's disease here in my example. So any disease you want to identify, if you want to identify maybe, like for me, when my paper on GERD, gastroesophageal reflux disease, I went to PubMed and downloaded all the abstracts that were in existence at that point. So that was from the beginning, which was 1970 something, to 2022. And that was about 39,000 abstracts, so which skyrocketed to over 300,000 plus sentences. And the keyword was GERD. So I was looking for sentences that had the word GERD in it. So if a sentence doesn't have the keyword GERD, it's kind of taken away. So that was a simple assumption. There are more complex assumptions that we can do in further research. So drug mention detection. So maybe if they mention a drug like ibuprofen, which is very common among all cultures, right? Metamorphin and so on. So these are use cases. Secondly, so we'll after this, we'll take a break after talking about this method. So there are 3 methods, and then we'll take a break. So relation extraction is the process of identifying and classifying relationships in entities of a text. So let me just take a diagram. So if this is a clinical note for a patient, John Doe. Now, this is how clinical notes typically look like, that are organized. These are organized clinical notes, not just jotted, right? Now, what we could do with relation extraction is that in a graph, we can easily now display most of this information that was taken here. Like, for instance, this is the date. The date is a very important in medicine, because we need to be able to track when a patient received treatment, how long, you understand, from when did you last take a prescription, should you take a new prescription. So now, instead of having this long thing, we can have this, and it's going to be very easy. So John Doe receives from this date. This doctor also prescribes the drug on this date. This Dr. Michael Brown treats John Doe. Alice Smith is the pharmacist. So Alice Smith basically dispenses the drug amoxil. John Doe takes amoxil, and then the date is just to connect all of them together. So if we really look at this, we're trying to extract relationships. So relationship extraction can be from just a single line, and it can also be from like an entire paragraph. You understand, an entire book. So you want to try to look at what are the important nodes, what are the key players in this game, right? We can see that the key players here are the patient, the date, the primary physician, and the pharmacist. You understand? Or if so, like medication too is also very important. We can also have added bacterial infection if we need, if what that is your use case. So this is just an example. You understand? It always depends on your use case. So that's why you have to formulate your research question before you begin to do this. So that's what relation extraction really looks like. So you're just trying to extract the relationship between entities in a text. So this is going to be very used in like, which was one of my favorite sentences, GERD causes heartburn. We have to be able to know, okay, what really causes heartburn? Is it only GERD? Is it this? Is it that? So this is disease symptoms relationship. And think about the 1,000 use cases you can use this in. Also drug target interactions, like aspirin inhibits CO or X2 enzyme. This is just maybe a relationship that you've extracted from a whole large body of text. So for instance, now what you do first, rather, sorry, you get the name entity recognition, you've gotten the entities itself. Now what you're trying to now do is now find the relationship between these entities. Do you understand? And this is a whole research field on its own. And then the final thing before we take our break is the entity linking. So, and the co-reference resolution. Have you ever thought about, I know today's election, nobody's voting for Obama again, so this was very safe to use. You understand? So is that I voted for Obama because you understand, he here refers to Obama. Now think about a complex sentence. You understand? Maybe someone is said GERD and then now uses it in a sentence. How would you extract that? So that's what we call co-reference. So it is referring to something that has already been referred to in the past. Now, when you're trying to do relation extraction, when you're trying to do name entity recognition, you're going to fall into this a lot. So you want to be able to identify context, you understand, which is very important. So that is a whole research field in biomedical and engineering on its own, and everything that relates to biomedical research with large language models and NLP. So you would, so that is just some slides that you can read. I think we'll share this. And then the use cases we can see in standardizing disease mentions, like type 2 diabetes is usually referred to as T2D, you understand, which is type 2 diabetes. So if imagine, like you see in a clinical note, you see type 2 diabetes and then in bracket T2D, and then for the rest of you, it's just T2D or things like just diabetes, because it's still referring to that. Now that's different. For instance, like I'm working on a knowledge graph on social science, and we see inflation, we see price inflation, and it's talking about totally different things, you know, and then you have to now relate to, okay, this is different, is using this word inflation, but this is not the inflation that we are considering. This is another inflation. So these are things that co-reference helps us. It helps us to standardize disease mentions. It also helps us to resolve patient mentions in case studies like the patient, he or she, and things like that are used. So we'll be taking a break now, and when we come back, we'll be talking about AI models for knowledge graphs in biomedical. Thank you. All right. So I'm going to continue talking about AI models for knowledge graphs in this field, right? So if we look at how AI has evolved over time, because AI didn't start when ChatGPT came out. All right, everyone's so let me tell you guys a secret. So when I was in 2022, when I started my master's, and I was encumbered with so much work because I was running 2 masters concurrently at that time. there was a lot of work to do actually, and a lot of papers to read, and a lot of research. And my advisor was not easy on this because I never knew what transformers was. I came from an electrical engineering background, and to me, transformers were those coily things that if it blows off, there'll be no light anymore, you know. And we have this phrase in Nigeria where it's like, go and hug transformer, which means that I don't care about what you say, you know. But getting into this field, I had to find a way where I could efficiently use the tools. I knew how to code, so I needed to know how to use those tools to help my research. And that's where I found GPT, not ChatGPT. That time, this was 2022, right? And then I found out that there was something called GPT-3, and we could all use it. So I used it and imported it into my system. We were giving like a 3-month trial for that. And then I started putting in the prompt of my introduction, and it summarizes it for me. And then my abstract, it does that. And then I was like, yay, see who is excelling in it, you know? And I felt like I was using something grand. And in a matter of months, ChatGPT 3.5 came out, and everybody went on the train of ChatGPT. But I always tell people that I was the first person to use it before it was ChatGPT. But before this, there were other methods that people had used, and one of them was rule-based methods and neural networks. A lot of people who have taken a deep learning class, or just basically any machine learning class, you would have heard of deep learning. And whenever we hear deep learning, especially when I was in undergrad, I always felt like it was so deep, it was so advanced because the name is deep learning. I felt like it was only for the smart people. And when I got to deep learning, I was like, this is easy, you know. I like the name deep learning because it makes people not want to go into the field. So there's more money in the field. Because if everyone is, if it's easy learning now, everyone will be going into it. Yeah, but rule-based methods basically has a rule, and I'm going to kind of demonstrate this here. So if we have this person who is querying, now this person can be like a doctor. Do you understand? Now this is just a new doctor. Think about a new doctor. Now this new doctor is going into the electronic records, and then this is the user interface. If we are in HCI, that's your field, right? But this person is knowledge expert. He has already poured all the knowledge he has. Now, this knowledge expert can be a whole database of actually peer-reviewed papers that say that this fact is true, and all this has been created into a knowledge base. Now, what rule-based method says is that if something is something, then we have this result. For instance, you know, if you see a genetic mutation in the BRC1 gene, you understand, then we can assume cancer. Or else, if something is this, you understand? So this is basically a rule-based. So it's really hard-coded. It's not really super efficient, but it is efficient because we can kind of use it for like a large data set that contains the same thing. But then when we throw in something else that is different, we basically have to run back to our code and try to update it. And this was what the rule-based method was all about. So we have the rule base itself. So this is the rule base. We have the inference engine, which is here, you know, and then this is the knowledge base. You understand? Then the user interface just communicates the inputs and the output. So another thing is, okay, so I had patients text data, inference engine. So for instance, this could be health records, could be social media posts. And then this could be like rule-based. If symptoms is chest pain and shortness of breath, you understand, then infer cardiovascular risk or something like that. And then this is what the doctor sees. You understand? So these are this is just applications of the rule-based methods. If we're now looking at machine learning and transformer models, which is okay, is to be part of the deep learning, we see transformer models like BERT and BioBERT. BioBERT was specifically trained on PubMed. So it's, let me just save you time. It does better among all the BERT family models on actual like medical data. So if you're in bioinformatics, it's easier for you to use BioBERT than any other model. It will perform better than that. I've read many papers on it. My paper too also showed that BioBERT actually outperformed BaseBERT and Roberta and some other models that we also tried. Now, like I said, BioBERT, a model trained specifically on biomedical text, offers distinct advantages for processing that kind of literature. But one thing we see in machine learning or deep learning is the concept of supervised, unsupervised, and reinforcement learning. Now, so I'll just kind of just briefly explain this. So supervised learning is when you have labels. You already know, like for instance, you know, you have some mammographs of breast cancer. Now, then you also know the people, did they have breast cancer or not? You understand? So yes or no. So you have this mammograph, does he have breast cancer, yes or no? And then you have maybe 10,000 of that. Now you put this into the algorithm. Now maybe a convolutional neural network. You understand? Now if you are doing a text, you write some text, you have maybe an output, and then you take it into the model, and then the model is trained. Then you put in fresh data, and then it predicts an output. Now, when we predict this output, we usually in the medical field, we are looking for about accuracy of 98, 99% before anything is majorly pushed to production. That's if you are going to be building an app, you understand, or creating something like that. Now, if you are maybe just doing it for a class project, you know, doing a 80% actually would suffice. You understand, because you don't have the resources to make it you understand, almost 100%, because the more data you have, the more advanced models you have, the better your prediction is going to be. But this is really going to help people, because imagine 99% of all data that goes into here can be correctly predicted. So when we see a mammograph, you understand, we know that, okay, this person has breast cancer. So we can actually really look into that, you know, and say, okay, the doctors can now look into the mammograph. Does this person really have breast cancer? You understand? At least we know that with this model, it can tell you what the result is. Then for unsupervised learning, you don't have the labels. So this is what we call clustering. You understand? So for instance, now taking the same breast cancer example, we don't know what if they have breast cancer or not. But now what the model does is that it now begins to look at maybe a pattern in each of those mammographs and say, okay, this section has a lump in this in their mammographs. This section don't have this lump. You understand? And now doctors can now begin to look into this and now begin to say, okay, this is the issue. Another example, which my friend here reminded me of, was the sickle cell. They found that sickle cell actually affects more African Americans than whites, the sickle cell disease. And when I came here into the United States, sickle cell is very common, like the knowledge of sickle cell disease is common in Nigeria. So I came to the United States and then I saw people getting married. They didn't even know that. They don't know what their genotype is. You understand? Like there's some very basic things. I'm like, how won't you know? You understand? Are you AA? Are you AS? You understand? Are you SS? Now, and I now realize that it's because many of them I don't struggle with this disease in general. And then what ML helped us to know was that they clustered people that had sickle cell disease. And they found that almost all those people in that cluster were African Americans or were Africans. So which meant that the machine learning model was able to identify a pattern that otherwise would not have seen. And then for reinforcement learning, this is just basically we have like a human in the loop or anything in the loop. So this is training data, this is the algorithm, maybe this is a cluster-based algorithm, and then it classifies it here. Then we have maybe an agent. This might be a person, this can be another model that tells you, okay, is this right? It maps what the model is saying. And this is most models that are actually pushed to production. You understand? So maybe supervised learning gave us 99% accuracy. We need 99.99% accuracy. So for every 10,000 cases, you understand, we only want to see maybe one person that had an error. You understand? And then this agent rewards or penalizes the model. So the model begins to retrain until it can really accurately predict properly. And then we have the final predictions. And this is what is right now in use in industry. So I just kind of just showed the X-ray data here, convolutional neural networks and predictions. So it will also look at language translation. For instance, maybe you end up working in a foreign country, you are bilingual, you understand? So if you want to build a model that can help to translate language from one way to another, this is the principle of what Google Translate works on. So with a weighted system, it can actually translate languages. Now, embeddings and transformers, I was talking, that's the new ones that start. Embeddings actually started about like 2014, 2015. Does anyone know the meaning of embeddings? I think I'm losing people here. This is a very boring section. Does anyone know the meaning of embeddings? No. Okay, so embedded, okay, you know.
Yeah, you assign the value to each text.
Word, exactly. So for have you ever wondered how machines understand this text? They don't. Let me just tell you. So they understand numbers. You understand? So for instance, now the word bank. So maybe you have bank. Can someone tell me what first comes to your mind when you think of bank?
There's the shore,
Huh?
the shore, like
Sure. You said money. See, good. So we have those things. Like I love money, right? That's the first thing that came to my mind. You know, so money, you know, where you keep money. So another thing too is the shore, you understand, the seaside. Another thing too is if you lived in maybe a place where there was not 24/7 electricity, power bank. You understand? You see, you understand. So those are like maybe power or electricity. Now, so the funny thing about embeddings is that embeddings take this words one by one, like just this bank, you understand, and just gives bank 19, maybe 17. That would be just the value in the machine. And then the machine begins to look at patterns, like it just sees the word D and begins to say, okay, so these are the patterns, and begins to kind of recreate those patterns. But it does not take context that money is different from money bank is different from power bank. You understand? And it's different from shore bank, which is like they are all, you understand, they all mean different things now. But when you are in a conversation with someone, you when you say, oh, I want to go rest at the bank, you understand, you can, oh, don't fall off the bank, you understand, you can obviously know that that is referring to shore. But if you say I'm going to the bank to collect my money, you understand? You know it is not Shore Bank. You know it is Chase. You understand? Now this is the way embeddings went. So embeddings, and then we have transformer models. So embeddings were like Word2Vec, Glob were very popular in those days, and they were used by machine learning. But now the transformer models came out. So BERT came out with a solution to this. So which was called the attention layer. So they decided that, okay, we're going to pay attention to context. BERT stands for bidirectional. So the B in BERT is bidirectional. So it looks at the context before and then looks at the context after, before giving a word bank. So BERT now helped us to say, okay, this money here is 1917, but this shore now is maybe like 4,281, and then this power bank can be something like 0176. And then because of the attention layer, it has attention layer inside. If you read the BERT paper in 2018, which is also what GPT and every other transformer model is using right now. It has over 130,000 citations. So you who knows, you can work on the next big thing, do you understand? And you basically are going to transform the field of NLP. Now, so with this encoder model, BERT, BioBERT, Roberta, all this worked on those things, but the only difference was that the data they were trained on, like BioBERT was trained on like a biomedical text, Roberta was trained on more of clinical notes and so on. Then we now have decoder models. You understand? Decoder models is GPT. So all the GPT series are all decoder models. It's just the architecture that you need to worry yourself about. But when you read the papers, maybe you'll be able to kind of understand the differences between what they call an encoder model, what they call a decoder model, and the combination of both. Because they are combined does not mean they do better. You understand? We all know that GPT-4, nothing compares to it yet. You know, use cases of this, we can use BioBERT in drug disease interaction and genomic research and mutation analysis. Now, I think I've really spoken much about large language models, and BioGPT is one great large language model that you can use for analyzing biomedical information because it was trained on that. You understand? So you would also want to look into BioGPT, and I also was able to give the different types of LLMs, and then I'll just tell you where LLMs are heading to. They are heading into this agents based approach where we have multiple LLMs doing work. So one LLM is telling you, like sometimes, have you ever opened like 4 tabs of ChatGPT? If you have done that, raise your hand. Like for one report, you just open like 4 tabs. You understand? You are querying it one. You are saying this one generate the ideas. You fine tune the ideas. You shorten these ideas that's fine tuned. You know, and then you make it more human. You understand? Or restructure it, and you know, you're just having this kind of endless loop. You understand? So all this. So this is where LLMs are heading to. So there are different kind of models like GPT, which is OpenAI, Llama by Meta. Me and my friend Kaushik are working on like an agent-based model right now. And from the paper, which was Sci Agent's paper, they used the paper, they basically created an agent-based system of like 4 or 5 LLMs, right, to be able to create new research ideas. And it will go to Semantic Scholar and scrape all the papers there and check our idea against those papers and say, okay, is our idea novel or is not novel? So, and with that, you never get to run out of ideas. You can just give GPT, tell it that, okay, I'm considering this topic and the relation to this topic, and then it runs in the background, and then in the next 1 hour, you come back and you say, oh, okay, I never thought of this. Good. And then you have your project. You understand? Never would you have to run into the issue of, oh, I'm thinking about this. And then you go to Google Scholar and you find out that the paper is there already. You know, if you're a researcher, you discover that every time you think of something new, someone in 2008 has done it. But then the good thing is that think about whatever you submit now, you know, someone in maybe 2030 will do it, and then they will think back and they say, oh my God, this person has done it. You know, so it's going to be like that. Overall, so this is just like me explaining what LLM agents will be like and how they take from the environment and they basically can analyze within themselves. So use cases, BioGPT can help with relationships like Alzheimer's disease, associated with tau protein aggregation and so on like that. And also for literature summarization. I love literature summarization because sometimes some people use so hard to read text. You know, the text is so verbose, and you wonder, like, this is not necessary. You can use simpler English. So I was just like, okay, so what is help me summarize the abstract, summarize the introduction, gives me bullet points, you understand? And I begin to read it line by line, side by side with the paper, and it helps me to finish reading a paper under 1 hour. So definitely a lot of people use this for I don't think anyone here does not use GPT for text summarization. Everyone does, you know. Yeah. So the guard knowledge graph construction is going to be the last thing that we're talking about. So and I think I've actually covered most of this. Is in my paper. So in case maybe you want to read that, I think they'll make it available to you. It's on ACM and it's also on my Google Scholar page. It's called Can Deep Learning Models Create Knowledge Graphs? And maybe if you are publishing a research, you can always cite the work if you end up using it. So the whole idea of this was I picked a topic which was GERD, and I said I went to PubMed, script all the articles, then had to do some cleaning, and I went through named entity recognition. I used Spacey to do the named entity recognition, which is one of those tools. So as you go deeper into each field, you begin to find out what you can do. Then after named entity recognition, I did my relation extraction and also my coreference resolution. And then after that, I began to train my BERT model to be able to identify those relationships between them. And before you know it, I had my knowledge graph. So that was how I was able to curate about 300,000 sentences in the space of 1 year. Yeah, 1 year. And it was a solo project, so it was an independent study. I, but it took time, but we're alive. So I'll be taking questions now. So if anyone has any questions, I would really like to hear them. All right.
One use, I think of this would be maybe, let's say you're trying to like do data mining, right? You want to find a bunch of data sets you could try to combine to get a novel result. Could you use a large language model to maybe like scan through PubMed, pull out, not only relevant topical, but also papers that actually have available data?
Okay, so can you give an example of
I
that?
mean, let's say I want to study, I don't know, heart disease, let's do microRNA heart disease. I want to combine data sets from a bunch of microRNA papers on heart disease. So I
Okay.
can do a, combined analysis more powered. Could it like scan, say, not only check, okay, microRNA heart disease, but also for data availability, like?
All right. I think there are actually like tools for that right now. I know Praneet showed us one tool like that. That you basically can put in a link of a paper, and then it can summarize like whatever is on the page of the paper. But I don't think large language models can like go all the way to check the internet, except they are fed in
Yeah.
that data itself. So what you can do for a case like that is to look up heart disease on PubMed, and then you can pull out all these articles there, right? And then you can train a model just based on sentences, just put that into maybe a model like GPT, and then tell it to bring out all the data sets that were used in these papers. So it can curate like a list of possible data sets for you. And then you will now go and check, because not all data sets could be available, but you might not have all access to it. So there's always patient confidentiality and some rules to many of those data sets. So but my advice to people is always use open source data sets. Typically, ChatGPT 4 already knows many of the open source data set that is available in 2023. So if once you query that, you'll be able to give you like this data set are things that are related to heart disease, and then you can check those data sets, and then you can now begin to figure out how you can combine them, because combination is always a very hard task when you're trying to work with multiple data sets. All right, I hope that answers your question. All right. Any other question? Okay.
Do big modeling in healthcare data or any library that you would recommend
Except for BioBird or Baby.
Um, try Medline, Biomedline, and also, if we're looking at just analysis, am I right? Analysis.
Topic modeling.
Okay, if we're looking at topic modeling, I feel like, yeah, I feel like it would, uh, I don't know why, I've said if you are going to look at BioBERT and Spacey, okay, those are like common, everyone uses NLP. You can also look at clinical BERTs, right? That's one, that you can also use, if the topic modeling is in, this field. Then also look at the decoder models like, GPT, look at Llama, look at Mistral. So those are things that you can actually use at this point. Hope that answered your question. Any? All right.
So I was just asking, like, how can embedding models like BioBird, like, how can we improve the matching of like different complex biomedical terms across like different ontologies using these embedding models?
I don't understand your question.
Like from different types of models and like frameworks, how can we improve matching using embedding models and BioBird?
Okay, so explain what the context of matching you're talking about.
Myself, I'm a little, like, I didn't really, it's just based on what you mentioned, like, I just found out.
Yeah, I'll summarize. So what she's asking is, there is a model, so
Okay.
there are different kinds of terminology. How that model get to know all this terminology and it makes sense. out of
Okay,
context.
okay, yeah. So, okay, yes. So typically, most models, especially BERT, fails in understanding those terminologies, like especially new ones. So what it ends up doing is that, for instance, like, let me use this pen. So something like gastro, gastroesophageal reflux disease. So something like this now, it can break the sentence into this and then put this here, and each of this will be different tokens. So when it's reconstructing the your response, it can kind of figure out that this embedding always goes with this embedding in all times. So it's always comes, so it's going to come out as a word. So not necessarily because it's been trained, because sometimes it doesn't really see this word. That's why sometimes when I was training with was it GPT at a point, it started coming up with new words that I've never heard, yes, I've never heard of before. So because this is the structure in which it is done. So I hope that answers your question. All right. Any other question? Okay. You have a question? No, okay. All right. So thank you.